Hi there. So this is just to give a demonstration of this emotion detecting neural network. So as you can see, I've got every single step that I've done along the way still in my code, just commented out. But this is just to give an idea just as to how this thing actually works. So I've taken I Hear an Army by Samuel Barber. I took a recording from my senior recital and I converted it into a WAV file. And so I'm going to have it go through a couple processes, and actually I'll add this on as well. So I'm going to have the vocal separator separate out the vocals from the noisy data, in this case the accompaniment, and then I'm going to have the two WAV files, the original WAV file, as well as the one that has the isolated vocals, which is this NA, or new audio. So we'll have two different splits going. So basically what this will do is it'll take the whole WAV file and divide it up into 20-second long segments, as you can see by this split length variable I put over here. After that, it's just going to run the prediction algorithm, and I'll put a little separator just so you can actually see here where those two start and stop. So let's run this. And it actually runs surprisingly quick for being what it is. That's not necessarily a normal case on most people's computers. It's just because I have a more powerful computer. Otherwise, anything involving running neural networks can be extremely slow. And all of these algorithms separating out the vocals, that's a lot of mathematical processing, separating out a WAV file. WAV files are huge, so it's just a matter of how powerful the computer is as to how fast this thing will run. And even with training neural networks, it's the exact same way. Training, depending on the amount of data that you're training something on, it can take, per evolution, it might take a couple seconds, it might take 30 seconds, for example, in my case for this process. But in other models that I've trained, I've had it take up to an hour, 2 hours, even more than that when I was training models on my laptop before I had a better computer. And that process takes a long time when you're training for 2,000 evolutions at a time, and you have to wait 2 hours in between. So yeah, this process can be very, very tedious. So right now, I'll scroll back up into this code so you can see what's happening here. This is after the vocals have been isolated. Separating the vocals out is the longest process out of all of this. So this is just the first split, so splitting the new audio with the separated vocals into 20-second segments. You can see the 0-second segment, 20 seconds in, 40 seconds in, all the way up until it hits, the last one. And then the second file starts, so the original file. And let's take a look at what it actually outputs over here. So this is just a little 5-second snippet of the audio spectrum. These hot yellow lines represent the voice in this case. So whenever we run our separation algorithm, we basically pull out two separate masks or thresholds of data in this case. So we have a background layer, which is mostly noise, and we have a foreground layer, which is mostly actual signal, or the actual voice in this case. Obviously this isn't always going to be 100% perfect. Separating vocals is a very difficult process, and this is just a very lightweight algorithm that I wrote, and even then it was a lot of code just to be able to do something like that. So after the vocals are separated, we obviously have the WAV file split, and then the actual prediction starts. So this is just loading up. So this is starting with the separated audio, so the isolated vocals. So it's loading up all of these different files that pop out in here, loads them up into the model, and this is just a summary of what the model actually looks like. So these are just the various different layers, convolutional layers, pooling layers, dropout layers, dense layers, all those different things. So the total parameters is the total amount of data that has been isolated from all these different files. That's something that we can actually use for training and prediction purposes. So in this case, these are the predicted values, and sadly they don't pop out quite in order. You can kind of see down here. So it goes from 0 seconds to 20, 40, 60, 80, being 6, 7, and 8. So obviously it's not 100% perfect in the way that it prints out, but we can say that at the very start of the song, it starts out neutral. At 20 seconds in, it's sad. 40 seconds in, it's calm. 60 seconds in, it's fearful. 80 seconds in, it's calm again. 100 seconds in, it's calm. 120 seconds in, it's sad. 140 seconds in, it's sad. And that's not too off of what I would expect from the actual song. I would say it's more angry than sad, but it depends on how you interpret it, I suppose. Which is what makes it a little bit difficult as to how accurate this thing is. And here's where it really gets different. So in this case, when the vocals were not separated, so it was just the audio and the accompaniment, the values change quite a bit. So we went from neutral to, let's see, this is 20, 40, 60, 80. Neutral to happy, happy, calm, 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 and sad. So, again, quite a bit different, but also a lot of these do overlap. Let's see, there's 4 instances of calm in the first one, 3 in the separated vocals, and it starts off neutral in both of them. Neutral, calm, calm. So only this one really changed in between. Actually, this one right here. So 60 seconds in, it was interpreted differently. And sad stayed the same. It was just happy and happy are different. So 40 seconds in and 60 seconds in are the only times that were interpreted differently. So let's actually listen to what those were quick. So that was 40, yeah, 40 and 60, right? Yeah, 20 and 40, my bad. So 20, 40, 60, 80. So let's listen to 20 real quick. So that's a more major part of the song. And again, that one's a little bit hard to decipher as to why it might have guessed happy. Let's listen to the actual file that it predicted. So again, it's not always perfect. I would say more often than not, it's a little bit more precise when the voices are isolated. Looking at the appendix of the research paper, you can see this exact same trend appear, as well as in the other video that I did interpreting the data of this model. So the other thing that we can take a look at quick, just for the fun of it, I'll comment this out, and actually I'll just get rid of this code quick. And I was running a test on Erlkönig before this, so I'll comment those out. And let's look at the real-time system that I made up. So real-time prediction, again, it's a little bit difficult with this. And let's clear out the real-time test. Okay, it's already empty. So how this works, I have a 5-second split length, and I'm recording for a duration of half of a minute. So If I wanted this to record for 2 minutes straight, let's say I'm doing a full song, I could set this to 2 minutes or 2.5 minutes, whatever I would want to do. And then if I wanted to be a little bit less precise, or I wanted a more broad overview as to when I'm getting predictions, I could change this to make a prediction every 10 seconds. But for this case, I wanted a little bit closer to actual real time. So let's get an idea as to what that looks like. And again, it's a little bit more problematic, I would say. So let's run this. I'm just going to keep talking over it. You'll see over time down here, most of the time that I really likes to predict angry when it isn't sure what to. I actually trained the initial model. I trained, and for whatever reason, the accuracy dropped down to like 2%, and it just started guessing angry for every single emotion. This only seems to happen when it has one single bit of training data to predict on. I'm not sure why that is, but let's take a look at what happens if I predict afterwards. So obviously right here, it just guessed that I was angry the entire time that I was talking. So if we run a prediction on the real-time test system, so let's look at the audio files that were recorded in entirety. So some angry still, some angry, more so fearful. I wouldn't say that I'm necessarily afraid of why it's predicting angry, but I don't know, maybe it's some innate unconscious acoustic feature that I'm not aware of in my voice. But I guess I was happy at 15 seconds in or 10 seconds in, whatever this may be. So again, these sorts of systems are really difficult, especially when you don't have a lot of training data or predicting data. There's a lot of things that can go wrong, and that's one of the biggest challenges of these sorts of things. But I figured I would give a brief little overview as to what this thing actually did, just for the fun of it. I'll give just a little test demo as to what's actually happening under the surface. So let's take a look at the demo feature. And once again, I'll comment these guys out. So let's take a look at what the demo feature actually does. And I would demonstrate the training algorithm, but that would take quite some time, and it would make this process a little bit longer than it needs to be. Let's actually, I'll do this with this file instead. Okay, so it's not actually putting anything out here, which always throws me off. But if we look into, let's see, audio files, we have test 1. Kids are talking by the door. So that's what the data actually sounds like from the database, RavDes. So that's just a little 4-5 second snippet, I suppose. And then let's come down to here, and the file that it output was wavetest1. So wavetest1.png looks like this. And what's the other one? Melspec. Melspec test1. So of that 5-second snippet, this is the waveform from 0 to 4 seconds. After that, this is what the actual spectrogram looks like. And that's what we have here in our longer snippet. But in this case, we're trying to get a better idea as to what's actually going on in between these features. Primarily, there's a lot of information that we can find in between 1,000 hertz to 2,000 hertz. Let's take a look at the demo code just to actually see what's happening up here. Okay, yeah, so we're just basically loading up the MEL spectrogram. So this is the full spectrogram of that audio snippet of I Hear an Army. This is the MEL spectrum. So the MEL scale basically takes it as to how we would interpret it for our ears. So this is basically a visual example of how our ears would hear that audio clip. And that's when it comes down to actually finding these power cepstrums, and that's basically what we're plotting out. The MEL frequency cepstral coefficients are essentially what we're looking at throughout this little data file. And that's really everything that I've got outside of just showing the basic training, which is a long process because there's a lot of things that go into it. All of these different emotions to interpret, and also over 1,000 audio files to test on. But yeah, that is the basis of this little prototype program. So a lot of interesting things, a lot of strange features and strange results, but as is the nature of things.